Hey guys, welcome to our lesson on section 8.4, parametric equations. So parametric equations are another way to be able to graph things. There's some really nice applications for them. One of the biggest obvious ones that we've seen probably numerous times is the old quadratic for throwing a ball in the air, or ball being hit, or anything like that. The nice thing about a parametric equation is it essentially adds in this third variable. And so what we can actually do is we can get a more detailed idea of what's going on by using parametric equations. We can actually have a situation where we have a time variable. We have one variable that represents horizontal distance and another variable that represents vertical distance by using parametric equations. And it makes it really easy and useful for us to be able to do certain problems. So let's get some definitions out of the way and we'll get going and practice with these. So a plane curve is a set of points x, y, such that x is equal to f of t, some function f with the input of t, and y is equal to g of t, where f and g are continuous functions on the interval from a to b. Okay? We say that the equations x equals f of t and y equals g of t are called parametric equations. Parametric equations with the parameter t. So what we have going on here is we have basically this curve is created by looking at the set of points x, y that create this graph, whatever it may be, and those are created by these continuous functions. Okay, so remember, flashback, continuous simply, the very simplest set means that you can draw it without lifting your pencil. Okay, so for example, if we think over here, if this is A, this is B, so to be continuous on this interval, say a function that does this is continuous. If a function goes like this, that's not continuous, right? And so that's really the simplest way to figure out continuity of functions on an interval from A to B. Okay, that's not really something you're going to be needing to figure out yourself. That's more so going to be something that will be an obvious thing in the problem, right? Most of the functions we've dealt with in all of math, right? Linear, quadratic, polynomials are all continuous functions. Rational functions have some discontinuities and things like that. Piecewise functions can have all sorts of discontinuities no matter what. So we want to be careful when we're using these parametric equations to figure out, make sure that they're actually continuous. For the most part, in this lesson, you guys are going to be deriving your own parametric equations. They'll be kind of built up for you. You may have to plug some things in and evaluate and figure out what those actual equations are. But for the most part, it's pretty straightforward. So let's fill out this table and let's kind of see what this graph looks like. So we're looking at x equals t minus 2 and y is equal to t squared plus 1. And notice it says with negative 1 is less than or equal to t is less than or equal to 2. It is possible to have t be everything. You could say t is all reals. But most of the time when we're doing a parametric equation, our parameter t is usually confined in some interval. Again, that's not always. It's absolutely possible and perfectly okay to do it without any limits. You could just simply say t is greater than 1, or you could say it's t is real. We just have to make sure that we're paying attention to what those limits are. So since we want to go from negative 1 to 2, let's start at negative 1. Let's start at negative 1. And let's go negative 1, 0. Let's throw a half in there for fun. 1 and 2. So those are the t values I want to evaluate this parametric equation at to try and get these points to give us what is our rough idea of a parametric curve. And so our first point here, so negative 1, x is equal to negative 1 minus 2, negative 3. Y is equal to negative 1 squared plus 1. which is 1 plus 1, which is 2. So that means when t is negative 1, we get the point negative 3, 2. And we just do the same thing going all the way through. Okay, so here x is equal to 0 minus 2, which is equal to negative 2. Y is equal to 0 squared plus 1, which is 1. So we get the point negative 2, 1. X 1/2 minus 2, negative 1.5. Or if you like, negative 3/2. 1/2 squared plus 1 is 1/4 plus 1, which is 5/4, or 1.2. So let's go with fractions. So negative 3/2, 5/4. Yeah, sorry, 1.25. There you go. So we just keep doing this, evaluating all these t values. So 1 minus 2 is negative 1. 1 squared plus 1 gives us 2. Negative 1, 2. And last, so we get these points here. Now, I want to sketch a graph, okay? So what we want to do is we really just want to simply plug these points into our graph, okay? We have negative 1, 2, 3, 4. 1, 2, 3. Okay, so our first point is negative 3, 2. Our next point is negative 2, 1. And then we have the point that's negative 1.5, 1.25. So negative 1.5, 1.25, negative 1, 2, and 0, 5. So we start here, and it goes like this. Now, the thing with parametric curves is they actually have a direction, because our parameter t goes smallest to largest, just like everything else, and that actually creates a direction on our function. And so because this started when t was negative 1, got us this point, and then when t was 2, it got us to here, we would say that the direction of this is this way. And this is how we typically label that. We put little arrows along our curve to signify that we are traveling in this direction. The reason why this is important is think back to the problem I kind of gave you at the beginning, where this is really useful, ball being hit, right? That direction would start at, not the origin, but, somewhere around there, right? When x is 0, and it would go out, right? We want to be able to have this situation model the ball kind of leaving where it's hit and going to where it lands, as opposed to starting from where it lands and, kind of reversing back. And so the parameter is really nice and useful that way. Let's do another example. Okay. Now here, instead of trying to just create a table and graph this, I want to find an equivalent rectangular equation for the above parametric equation. And when I say rectangular equation, what that means is our kind of standard, y as a function of t kind of equation, or you can do x as a function of y as well, right? So these don't necessarily have to be, parametric equations are not necessarily, if you look at their overall resulting graph, that may not be a function, right? Parametric equations are really useful in graphing circles and other sort of shapes like that, ellipses and stuff like that. It's really useful to do that. And so don't expect the end graph to be a function. The only thing that is required is that it's a function that defines x and a function that defines y. But the end does not have to be a function. And so when we get a rectangular equation, it could very well be something like x equals y squared, which, if you're not sure what that looks like, it looks just like sideways parabola, which is very much not a function. So how do we find a rectangular equation for the above parametric equation? What we're really doing is we are wanting to look at kind of where these two functions are simplest to deal with. What our goal to do, so let me make a little note. So, to find a rectangular equation, solve for t. Not in both, but in one. And so we want to see which one's simpler to do, and that's obviously in this problem the x. So to do that, we just add 2 to both sides. And we get that t equals x plus 2. Okay. So now we're going to use this equation twice. The first thing we're going to do is we're going to replace t with x plus 2 in our equation for y. And when we do that, we get y equals, instead of t squared, we get x plus 2 squared plus 1. If I square x plus 2, I get x squared plus 4x plus 4, and then we have our plus 1. That gives us our final equation of x squared plus 4x plus 5. Okay, now we're not done. And the reason we're not done is because this right here, I'll bring the y down. This right here is a function that is defined for all real numbers, so negative infinity to infinity. But we had a parameter that t went from -1 to 2. And so what we have to do, is we essentially are saying that, okay, so since t, so we have -1 is less than or equal to t, less than or equal to 2. But t is equal to x plus 2. So we get that -1 is less than or equal to x plus 2 is less than or equal to 2. So we have to solve this system of inequalities, right? So we essentially have two equations. If you imagine kind of, that didn't work. I was hoping that would just cover things up. If you imagine covering up this right-hand piece, the less than or equal to 2, we have the inequality -1 is less than or equal to x plus 2. Cover up the right-hand piece, we have x plus 2 is less than or equal to 2. We need to solve both of those. And luckily, because we have no multiplication or division, we're just subtracting 2. We can just kind of do this little nice cheat, subtract 2 from all three pieces. That cancels out. We get -3 is less than or equal to x is less than or equal to 0. And so what we get is that the rectangular equivalent to this parametric equation is y equals x squared plus 4x plus 5 with the condition that -3 is less than or equal to x is less than or equal to 0. So this is our final answer. Okay. So now, what if I want to graph this? Okay. We've talked about graphing these, and we've seen how to do it using a table. If we convert this over into a rectangular equation, and it's something like this, we could graph x squared plus 4x plus 5 using our calculator in the standard graphing mode. But what if I want to graph it, say something like this next one here? I want to use my calculator. And so the first thing we have to do, so to graph parametric equations in a TI 83 or 84. Okay. Step 1. Set the mode. Okay. To do this, just the same way we changed mode for radians and degrees. Okay, so if you press mode, I'm going to write just the first few things. You'll see the first word of each line. So it's a normal, float, radian, func, and then this is the line that we're worried about, or we're concerned with. And we have pair, polar, sequence. So these are the 4 types of kind of function modes that your calculator can deal with. And if you look at the variable button, right? So the button we use for variables when we type our y equals, this is kind of a side note, right? That variable button says x, t, theta, n, right? That's one button on your calculator, okay? The reason for that is x goes with function, t goes with parametrics, theta goes with polar, n goes with sequences. So what we need to do is, because we're dealing with parametric equations, you need to have this highlighted. Once you do that, okay, you could quit or whatever, go to the y equals. Okay, so once you do that, step 2, go to y equals. And what you're going to see on the screen, you'll still see the plot 1, plot 2, plot 3 at the top. But now what you're going to see on the screen, and this is what it should default to. This little first symbol could be a little different depending on if you've done weird things. See that, and then you should see x1 t equals y1 t equals, and you'd see x2 t equals y2 t equals, and so forth. And what these are is these create a polar equation or polar curve, planar curve. Okay, so if we wanted to type in, say, that first function that we dealt with, right, this one here, and you wanted to see what it looked like. So x is t minus 2, y is t squared plus 1. So in x, we would have t minus 2, and in our y, t squared plus 1, okay? And once you've got those typed in there, the next thing you need to do is hit window. So go to window. Okay. The first thing you should see is t min equals, and then t max equals, and then you'll see a t step. The t min, t max, that is setting our limit. So to graph this very first equation that we already graphed, the minimum t value was -1, and the max was 2. Now the t step tells us basically your calculator how often it wants to pull a point from these two graphs to plot on here. If you say set it to like 2, you're going to get a real chunky graph. And let's look back at our table. Okay. If we did every 2, it'd start at -1, and then it would do it at 1, and then it would do it once again at 2. And so it'd go -3, 2, -1, 2, 0, 5. So it would almost look like a straight line and then go up. It wouldn't actually get this curve. So you want to make sure you have enough kind of in the t-step. 1 is pretty safe. 0.5 is better. 0.1 is what I believe it defaults to most of the time, and I usually like to keep it at 0.1. Your calculator can do things pretty quick. If for some reason you do this and it looks just a little off, it doesn't look like what you expected, make that 0.01. And then from there, make sure your x min, x max, let's just do them standard, so -10 to 10. Okay. And then just hit graph. And you should see that curve generate. And what you should also see is you should see the way it generates is in the same direction that should be flowing. Now you don't see the arrows here. And that's just kind of how it goes. And so, but you can see when you hit graph, you can see the direction it goes. So it's always nice to pay attention when you hit graph, don't just look at the end result. And so once you've got all this, step 4, hit graph. Now, remember, these are the steps for an 83 and 84. If you have a different calculator, you need to Google the steps for yourself, look at the manual, or come and ask me. Now, let's look at example 3. We now know how to use our calculator to do this. Okay. We can now use that to check what we do at the end. So graph the parametric equations given by x equals 3 cosine t and y equals 3 sine t, where 0 is less than or equal to t is less than or equal to 2 pi. Now, I know it doesn't say it on here, but we can see very simply that we need these to be in radians. Okay. So we want to make sure our calculator is in radian mode. So if it wasn't already, put it in radian mode. It should be in parametric mode. Let's use our calculator to do this. Okay. Because we're going to get some weird things, right? We know if t is pi over 2, we're going to get some roots and stuff like that in our values, and that's hard to kind of graph. So let's do it ourselves on our calculator. So x is 3 cosine t, and y is 3 sine t. Okay, our window, we want to set that up so our min should go from 0. Our max should be 2 pi. And when you do that, if you just type 2 and then the button pi and then hit enter, it's going to automatically do that calculation. It's going to give that decimal, that 6.283, continue a decimal forever. Do that. Do not just go like, oh, 3.14 times 2 is 6.28. Call it good. Make sure you guys actually use 2 pi in this value. Once you do that, hit graph. And now here's where things get a little strange. When you hit graph like this, if you had your x min and x max set to negative 10, 10, negative 10, 10, this is going to look like a little squish circle. It's going to look like a little oval, but it's not. And the reason it's not is because if you look at your screen, it's a little wider than it is tall. So what I want to do here, is we need to go to zoom. And then option number, it should be option number 5. And that should say z square. And so what that's going to do is it's going to change our window so that it is squared out. In other words, kind of one tick mark up is the same number of pixels, if you will, for the calculator as one tick mark to the left or right. And then if you want to, you can zoom in, get a little bit better picture, which if you just zoom in, it's going to give you a little too close. Negative 5 to 5 is pretty good. You do that, you hit graph. Again, it's going to give you that oblong. And then just zoom square from there. And we can see a little bit better. So what I always do when I'm doing these is I set my window to be what I think I need to have. So like in this case, when I zoomed in, it went too close. I couldn't see the ends. So I backed it out to negative 5 to 5, negative 5 to 5. And then I said zoom square, and it squares it up for me. And that's always a good idea. Get comfortable in doing this zoom and then the 5th button, or if yours is different than what I've got, whatever it is to square, do that. And what we should see that was terrible. Okay, that's a super terrible circle, but you get what I'm saying. So this is a circle with a radius of 3. And if we look up here, that totally makes sense, right? Because if we think about the unit circle, right, in the unit circle, we have a radius equal to 1. And we know that cosine of theta is equal to x, and sine of theta is equal to y. So if we have a parametric equation that incorporates all angles in one full rotation, and so that's really nice. That's a really cool thing we can do. So we can say that a circle centered at the origin with a radius of r can be given by the parametric equation or equations x equals r cosine t, y equals r sine t, 0 less than or equal to t less than or equal to 2 pi. Okay. And that is a really cool, easy thing to do. Now, how do I get the rectangular version of this? Now, if you know the rectangular equation for a circle, that's awesome. Okay. But what if you don't? What if you don't know the rectangular equation for a circle? Well, let's do a little exploration. Cool. I've got a very small room, so I'm going to do it right here. Let's just consider x squared plus y squared. Okay. Well, that's equal to, since x is 3 cosine t, that equals 3 cosine t squared plus 3 sine t squared. So then what we can do is we can simplify these things. And so we end up with x squared plus y squared. And since 3 and cosine t are multiplying, we end up with 3 squared, which is 9, times cosine squared t, plus 9 sine squared t. And if we recognize that there's a 9 in both, we can do this, and we can factor that 9 out. And now in parentheses, that's a really nice thing, right? We know what that is. What happens when I add cosine squared t plus sine squared t? It's 1, right? This equals 1 from the Pythagorean identity, right? So then this is our rectangular equation for a circle centered at the origin with a radius of 9. Now, what if we're not centered at the origin? Quite frankly, I don't care. It's not something I'm going to ask you to deal with. We're going to center everything at the origin because it's just the most practical and useful thing. We'll do an example, a fun little example with our calculator here in just a minute. That will be shifting some things around to make a big giant mess. And you'll see kind of how we move things around. But I'm not going to give you a generic how to move things because it's just not necessary. So now I want to find a parameterization for x equals y squared minus 4y plus 4. There's two ways to do this. One way is the simplest, kind of most simplistic way to do it. And honestly, for everybody here, this is probably the way you're going to do it every single time. But I'm also going to give another possibility just so that you can kind of see how it'll look. So the easiest way, we'll say the simple way. So notice how this rectangular equation is an equation for x given in terms of y. So if you think about this, y is our kind of more complicated. It's the kind of essentially the input variable it looks like. So what we say is, okay, y equal t. If y equals t, then that means x is equal to t squared minus 4t plus 4. That's it. That's all it is. Super easy. But another way is to recognize that y squared minus 4y plus 4 is actually y minus 2 squared. So if we do that, then we can set t equal to y minus 2. Okay. So then, very simply, if t is y minus 2, then x is just going to be t squared. And y is going to be t plus 2. Think of just adding this 2 to both sides, and we get t plus 2. And for both of these, we just say t, so that, let's say negative infinity is less than t is less than infinity, right? So that's how we do that. Let's parameterize another equation. Okay. Let me find a good equation for you guys. I don't want to do something that's going to be all janky. So let's parameterize y equals 4 minus x squared. Now, a super easy way to do it again would be just to say, okay, well, so t equals x, right? All right, let's flip it around and make it a little better. X equals t, therefore y equals 4 minus t squared. Okay. And that's really the easiest way to do it. Honestly, this is the way everyone's going to do it. Now, what if I were to say, okay, well, what if I do something different? What if I want to be fancy like the other one? Well, we look at this, and this you should be able to recognize this is a pretty simple factoring. It's a difference of squares. So that means we could rewrite this. I'm just going to do this as 2 minus x times 2 plus x. But notice this doesn't really lend us to anything nice. It doesn't really give us any quick, easy things. Like over here, it gave us a little simpler one. And so this is really the way I would do this. And again, negative infinity is less than t is less than infinity. Okay, keeping it really simple. Okay. Now, let's move on to this idea that I talked about at the beginning of the lesson. This moving an object through space, something being hit in the air. There's this whole big heady derivation of these formulas. Not worried about that. These are something you can write down. If I give you a problem that requires you to do this, I'm most likely going to give you these equations, either the final equations, or I'm going to give you everything you're given here. Okay. But make sure you have this written down in your notes, because remember, everything is open note, open book. So if I forget to give you these things, you still should be able to come here and figure it out. So, or let me say, if I choose not to give you them, it's because I want to make sure that you come back to these notes. So, neglecting air resistance. So this is a big thing in mathematics, especially at this level. Everything's in a vacuum. Air doesn't slow things down. We're being air resistant, neutral. So it can be shown that the path of a projectile at time t, launched from an initial height h with an initial velocity v sub 0 and at an angle of elevation alpha, can be described by the vector valued function r equals v sub 0 cosine of alpha times t times the unit vector I plus v sub 0 sine of alpha times t minus 1/2 gt squared plus h times the unit vector j. This all seems really crazy. Like, wait, why are we dealing with vectors? I thought we were dealing with parametric equations. We are. You're going to see how we deal with this in a parametric way in just a sec. Basically, you take the coefficient of the I and the coefficient of the j, and those become your x and y parametric equations. Okay. So g here is the acceleration due to gravity, which, depending on which system you're dealing with, is either 9.8 meters per second squared, if we're talking about the metric system, or it's 32 feet per second squared, if we're talking English system. So our good old fashioned miles and feet, right? So what we're given, so the problem statement has to give us the initial height, the initial velocity, angle of elevation, and then what system we're working in. Okay. If we're given those, okay, now we're going to assume English system because that's what we're going to write in most of the time. Okay. If we're given those, we can create the parametric equations very simply to be x equals v sub 0 cosine alpha. Let me back that up. Times t. And then y is equal to v sub 0 sine alpha times t minus 16, because 1/2 times 32 is 16. So minus 16 t squared plus h. Okay, now what's really nice is these v sub alpha cosine theta and v sub alpha sine theta, those are fixed values. So those aren't something that's going to be changing and going crazy or anything on us. These are just very simply a fixed value based on what our initial launch velocity is. Okay. So that is kind of our derivation of this, or kind of derivation from what we're already given. Let's do an example. So if a baseball is hit from a height of 4 feet at a 30-degree angle above the horizon, its initial velocity is 128 feet per second. We want to first, A, write parametric equations that model the flight of the baseball. So remember, what we needed to be given was its initial height, its initial velocity, and its angle. Okay, we were given the initial height, the initial velocity, and its angle. Now the other thing is well, what are we in English or metric? Well, look at the units. We're talking about feet here, feet per second. That's English system. If we were talking about meters, right, our height wouldn't be 4, it'd be something meters, and we deal with that. So we are going to use these two equations that we just created. This one here and this one here. And so what we want to do is fill these values in. So x is equal to v sub 0 cosine of alpha times t. Our initial velocity here is 128. Our angle is 30 degrees, and multiply by t. You want to grab your calculator, use the unit circle, whichever is easiest for you. Okay. Making sure you're in the correct mode. Right, cosine of 30 degrees gives us root 3 over 2 times 128. Okay. Gives us 64 root 3 times t. Now, if you used your calculator, you're going to get 110.85, and you're like, how did you get 64? Well, let me back up a step. Let me fill in. Like I said, you could use your calculator or you could use your unit circle. Unit circle is always nice because it's exact if it's there. Cosine of 30 degrees is root 3 over 2. 128 divided by 2 is 64. So we get 64 root 3 t. Okay, so that's our x. Now, y is equal to this bigger equation, this v sub 0 sine of alpha times t minus 16t squared plus h. So we have 128 sine of 30 degrees times t minus 16 t squared plus 4. So sine of 30 degrees is 1/2. So this is just going to be 64 t minus 16 t squared plus 4. You may want to write this like this, but it is not necessary. Okay. Now, what about our parameter? What does t go? How big is t? Well, because we don't know anything about when this stops, we don't know the end point, what we simply say is that t greater than or equal to 0. Okay, so that gives us that combined with one of these two, give us our parametric equations with our limits on our parameter. Now, as we develop this more and we figure some more things out, we can actually simplify this process. Not simplify, but we can further perfect this to give us an end limit on t, but I'm not going to worry about it right now. So what's really cool with this okay, is if you think about graphing this, our x variable here is very much like the horizontal distance. And the y variable is very much the vertical distance. And t is our time. And so what happens is ball is hit at 4 feet, right? I don't know exactly what our numbers are going to be, but it's going to go up and come down. And this is essentially exactly the same as if we were to get parallel to the path of the ball and look perpendicular at it. So if you were saying, let's say this is a baseball field, for those of you who know baseball, the ball's hit right here, we are looking directly at the side of this baseball. Okay, or this is a baseball, right? Yeah. Okay. So it's really cool because we can see both how far and how high it goes based on this. Whereas in the past, where we've had equations that give us a very similar graph, the difference was that this wasn't horizontal distance, but time. Okay. And so we didn't know how far the ball went. We knew how high it went and after how much time, but now we can know how far it goes as well. And so that is exactly what we're going to do here in part B. Determine the horizontal distance the ball travels in the air, assuming the ground is level. It's always, again, we're assuming we're in a vacuum. We're ignoring air friction. We're also going to assume things like the ground being level, right? Because if there's a big hill, it's not going to go as far. If there's a big uphill, it's not going to go as far. If there's downhill, it's going to go a lot farther. So we're going to assume level ground. And so what we are looking for is the horizontal distance. Now, how do we figure that out? Well, the ball hits the ground here, right? That's pretty safe to assume, or safe to understand. How do I find that? If I can't really plug anything into the horizontal, right? So I can't like set x equal to something. But what I can do is I know the vertical distance at that point will be 0. So what I can do is I can set y equal to 0. So we get the equation 0 equals, I'm going to stick with, we start 64t minus 16t squared plus 4. Now, if you look at these, all 4 of these are divisible by 4. So if we factor that 4 out and kind of divide it away, it just kind of goes away. So this is the same as the expression 16t minus 4t squared plus 1. Now, how am I going to solve this? Right? I don't want to try and factor this. So we use our lovely quadratic formula. So our b value is actually the 16. So we have negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Now, use your calculator. Carefully type this in. This is not something that should be new to you guys. You should be able to do this very easily. We get negative 0.1 approximately, and we get approximately 4.1. Okay. Now these are t's, which this means this is in seconds. So this means the ball is going to hit the ground at approximately 4.1 seconds. So if we know when the ball hits ground, now to figure out the horizontal distance, we just plug that into x. So we get that x is equal to 64 root 3 times 4.1. And when we do that, we get approximately 454.5 feet. Bam. That's it. That's all we have to do. Okay? I know it says all we have to do. We did a lot, right? What it really relies on is it really relies on understanding what's happening here. Okay? Remember that this is a parametric equation, so we're actually having kind of a directionality to it. And it really is the flight of the ball. Now that looks kind of like a baseball. Or part of a baseball. And so understanding the question asks how far the ball travels horizontally. We understand that to be, okay, well, how far did it go until it hits the ground? Okay, so to do that, we need to find out when does it hit the ground, and we have to figure out which equation best suits us to find that. And that is the vertical distance here. Okay. Part C is even easier. What's the maximum height of the ball? Well, the height of the ball is given by y, so we're focused on the equation y equals 64t minus 16t squared plus 4. That is a quadratic function, which means to find the max means we're looking for the vertex. So we remember that the vertex is at the point negative b over 2a f of negative b over 2a. So that means I simply go, okay, well, negative b over 2a is negative 64 over 2 times negative 16, and that is 2. So that means the height of the ball, the maximum height, occurs after 2 seconds. So I just need to find what that height is. So 64 times 2 minus 16 times 2 squared plus 4 gives us 68 feet. There we go. All right. So looking at this last piece, this is it. This is the end. We're almost done. Would the ball clear a 25-foot high fence that is 400 feet from the batter? So we have a few things going on here. Would the ball clear a 25-foot high fence that's 400 feet from the batter? So what we're really wondering is, after the ball has traveled 400 feet, will its height be greater than 25? Okay. We know from earlier problems that the ball travels a total distance horizontally of 454.5 feet, roughly. So we know it goes further than 400. So we know, it's not like, oh, the ball only traveled 300 feet, so no, it won't, right? So what we need to do is we need to figure out how long until the ball is at that 400-foot mark. So that's a horizontal distance. So what we need to do is we need to solve, when does x equal 400? When does x, why is it doing that? Okay, when does x equal 400? So we get the very simple equation of 400 equals 64 root 3 t. Divide both sides by 64 root 3. And we get that t is approximately 3.6. So it takes approximately 3.6 seconds for the ball to get to a horizontal distance from the batter of 400 feet. So now all we have to do is figure out, okay, what's the height of the ball after that amount of time? So we're finding y, so that's 64 times 3.6 minus 16 times 3.6 squared plus 4. And that is approximately 27 feet. So what this tells me is that when the ball has traveled a horizontal distance of 400 feet, it will be at a height of about 27 feet. So that is enough to clear the 25-foot high fence. So yes, ball will clear the fence. All right. Now you may be thinking, yay, I'm finally done. Woohoo, let's stop this lesson. But let's do something fun real quick. Let's draw a smiley face in our calculator. So what we want to do is a few things. Okay. So the first thing that you got to do is make sure that your calculator is in radians mode. And make sure it's on parametric. Okay. And then I want you to go through and clear out any equation that you had already put in there. Okay. And so what we're going to do is we're going to create, for the head, I want a circle centered at the origin with a radius of 2. Okay, we already talked about how to do this. I want you guys pause this video, write the parametric equation for this circle centered at the origin with a radius of 2. Pause the video now. Did you pause it? All right. Welcome back. Good job. For those of you that paused it, looked it up, good job. It should be really easy, right? We can just copy the equations that we had from example, I believe, 3. And so we very simply get the equation here is x equals 2 cosine t, y equals 2 sine t, 0 is less than or equal to 2 is less than or equal to 2 pi. Perfect. So type that into your calculator. 2 cosine t over 2 sine t. Bam. Now, the eyes. Eyes are also circles, okay? But we need smaller circles, and we need to know where to put them, okay? So I'm going to do the right eye, and then I'm going to have you try to do the left eye. So for the right eye, what we're going to do is we're going to have a radius of 0.3. Okay, the reason why is it just fits well within our circle, so it's just nice. And so we can model this. And so what I'm going to do is I'm going to have this circle centered at the point 1, 1. And so to do that, our x is going to be 1 plus 0.3 cosine t. And our y is going to be 1 plus 0.3 sine t. Again, 0 less than or equal to t less than or equal to 2 pi. And so this right here gives me the right eye. And what about the left? How would I get for the left eye, how would I get it to be centered at negative 1, 1? Well, it's very simple. The only thing that changes is the x, right? Because we want it to be a negative 1, 1. So it's going to be x equals negative 1 plus 0.3 cosine t, and y is still just 1 plus 0.3 sine t. So that right there, these two sets of parametric equations should show you how to move the center of any circle and kind of where it goes to. It's really pretty easy and pretty nice. Okay. Now for the hard part, the mouth. How do I get the mouth? Okay. Now, mind you, none of this is something that I expect you to, if I said graph a smiley face or a frowny face, I'm not expecting you to be able to do this. This is just a fun thing that we can do together. Okay. So for the mouth, we only want the lower half of the circle. Now the problem is we need t to go from 0 to 2 pi for these other pieces, for the head and the two eyes. So, and we can't say, okay, for these parts, have t go from 0 to 2 pi, but for this part, have it only go from pi to 2 pi, right? Because we just want the smiley face, we want the bottom half. So what we have to do is we have to figure out a way to affect the input of our cosine and sine function to deal with this. And this is through some trial and error, some guess and check, absolutely. What we end up with is we end up with the equation x equals 0.5 cosine of 1/2 t, and then y is negative 0.5 minus 0.5 sine of 1/2 t. And so what this does is this will give us only the half of a circle. That's what the half does. But notice that over here on y, it's minus 0.5 sine. And what that does is it essentially flips the y value to give us a smiley face. If that was plus, we'd end up with a frowny face. Okay. Now, What about our pupils? How do I do pupils? Pupils are easy. Okay, this, if you've taken a stats class, you definitely know how to do this, but really it's any sort of regression which you've done, should have done in other classes. So you're going to go to stat, edit, actually, not X and L1, L2, right? We want our eyeballs to be at 1, 1 and negative 1, 1. So negative 1, 1. So we do that. Okay. Now, here's the last part that you may have to do, and that is second stat plot. Turn on your stat plot. And what I want to do is I want to go to the mark and change it to the little plus sign. So stat plot. Then choose plot 1. Turn it on. And then the mark should be the second one in. It should be the little plus. Okay, so we've done all that. So let's type all of these equations into our calculator. So we've got, let me zoom back out a little bit so you guys can see. We've got, there we go. Okay, so we've got 2 cosine t, 2 sine t is our head. Okay, for our right eye, it's 1 plus 0.3 cosine t and 1 plus 0.3 sine t. For our left eye, it's negative 1 plus 0.3 cosine t and 1 plus 0.3 sine t. Okay. The mouth is 0.5 cosine of 1/2 t. And our y value is negative 0.5 minus 0.5 sine of 1/2 t. Okay. Have all of those in there. Now remember, you guys have to set up your window. There we go. Okay. Now, what we want to do for our window is kind of up to you. Okay. But the easiest way to do this is to take our x values. So our t min, right, needs to be 0. T max is 2 pi. And let's take our t step and let's do that as 0.01. Let's really get all of these points in here. Okay. Then our x, we're going to go negative 3 to 3 steps by 1. For our y, negative 2. Let's do negative 2.1 to 2.1. Again, steps of 1. The reason I'm doing that 0.1 is because our circles are radius 1, so I don't want it to come at the very, very tip. So, and if you want to change these, you totally can. This is just what I found works pretty well. And then once you're ready, hit graph. Your dots should be there. You'll slowly see the head start to form. It's going to take a minute to get all of this stuff going. There's a lot going on, especially doing our steps at 0.01. Makes it so that it takes a little bit longer to graph these things. But if you just put your pencil down, take a deep breath, and wait a tick, you will slowly see a face form on your calculator. It's very slow. All right, so that's it. Hope you guys had fun with this. Hopefully you got to see some fun things with this. Next section, 8.5 will be polar equations, yet another way to graph things. So I look forward to doing that with you guys. And with that, that's the end of it for me today, guys. You guys have a great day, and I'll see you next time.